Bismillahirrahmanirrahim. Assalamu alaikum everyone. I am Atya Shafiq from University of Management and Technology, Sialkot. Today I am going to presenting my presentation topic on Chemisorption and Physisorption. First of all, contents are abstract, introduction, adsorption, physisorption, chemisorption, factors influencing adsorption, techniques for investigating chemisorption, techniques for analyzing physisorption, comparison between chemisorption and physisorption, adsorption isotherm, Freundlich adsorption isotherm, Langmuir adsorption isotherm, applications of adsorption, applications of chemisorption and physisorption, and the last one is references. Now the abstract is scientists have been studying adsorption at different surfaces for a long time. This process is crucial for many important practical purposes in technology, the environment and biology. It's widely used in industry and environmental protection. When substances stick to a surface, it's the first step in many chemical reactions. We also use this process to separate mixtures like cleaning water and air. Some technological advancement in adsorption have come from trial and error rather than deep scientific understanding. Scientists are trying to bridge this gap between theory and practice. Recently, there have been big advancement in understanding adsorption, especially at the molecular level using computer simulations and new techniques to study surface. New types of material have been developed for adsorption like activated carbon fibers and nanoporous material. These materials are exciting for their special properties in science and technology. While studying of adsorption had a bumpy start before 1980, it's now considered a well-defined branch of physical science. It brings together chemistry, physics, biology, and engineering. This article covers the history of adsorption and the types of adsorption. Now the introduction is countless processes happen at the border between two different things, and some of them start right there. When a substance concentration changes at this border, we call it adsorption. Depending on the types of thing at this border, we can think about this process in different situations. When a liquid meets a gas, when a liquid meets another liquid, when a solid meets a liquid, or when a solid meets a gas. Most of the progress in using adsorption in big industrial application focus on situation where a solid meets a gas or a solid meets a liquid. However, in various lab techniques for separating substances, all types of interfaces are used. In this context, the word fluid is often used to mean either a gas or a liquid that's in contact with the surface of a solid. A fundamental concept in adsorption which happen at every interface is the real adsorption system. Let's look at this concept in the context of the solid gas interface. The real adsorption system is an equilibrium situation where the adsorbent is in contact with the bulk phase and a special layer at the interface. This layer has two parts: the gas that's close to the solid surface due to its force field and the surface layer of the solid itself. The term adsorption refers to the process where molecules accumulate in this interfacial layer, while desorption is the opposite process where molecules leave this layer. Adsorption hysteresis occur when the adsorption and desorption curves don't match. In such cases, the adsorption graph forms a loop that varies in shape depending on the specific adsorption system. Hysteresis loops are mostly seen with mesoporous solids, particularly when capillary condensation happens. The material in the adsorbed state is called the adsorbate, and the material in the bulk, gas, or vapor phase before adsorption is the adsorptive. When the adsorbate molecule penetrates into the solid material, it's termed absorption. The term absorption, along with its related term like sorbent, sorbate, and absorptive, is used when it's not easy to tell if it's adsorption or absorption happening, or when both processes occur at the same time. Now the types of adsorption. Adsorption can be categorized into two types based on the nature of the substance being deposited and adsorbed. First one is physisorption and second one is chemisorption. Here is the diagram. Physisorption Physisorption, often referred to as physical adsorption, represents an exothermic phenomena. It is characterized by a relative low adsorption enthalpy, typically ranging from 20 to 40 kJ per mole. In physisorption, gases are typically attracted to the solid surface primarily through weak forces, especially the van der Waals forces. Physisorption lacks specificity as the adsorbent does not exhibit a particular affinity for a specific gas. This type of adsorption is characterized by its reversible nature, meaning that the process of gas adsorption onto a solid can be reversed, returning the gas to its gaseous state from the solid state. When a gas and a solid interact, they can produce either a solid or a gas while generating heat. An illustration of physisorption can be seen in the adsorption of gases such as hydrogen and nitrogen at lower temperatures onto the surface of an adsorbent like charcoal. Physisorption is influenced by the surface area of the adsorbent. With an increase in surface area, the degree of adsorption correspondingly rises. For example, finely divided metals and porous material exhibit a substantial surface area, making them effective adsorbent. Furthermore, the nature of adsorbate, referring to the type of molecular species or substance being adsorbed, also plays a crucial role in this process. Here is a figure where gas molecules are adsorbed on charcoal atom. Chemisorption, also referred to as chemical adsorption, involves the adsorption of a substance that forms chemical bond with the adsorbent. This type of adsorption is highly specific, occurring only when there is a chemical bonding interaction between the adsorbent and the adsorbate. Chemisorption is characterized by its irreversible nature and preference for high pressure condition. The formation of chemical bond in chemisorption results in a high enthalpy of adsorption, typical ranging from approximately 82 to 40 kilojoule per mole. It's noteworthy that physisorption, which occurs at lower temperature, can be transformed into chemisorption at elevated temperature. Chemisorption is influenced by the surface area of the adsorbent, and an increase in surface area leads to an increase in chemisorption. An instance of chemisorption can be observed in the adsorption of gases such as hydrogen and nitrogen on the surface of adsorbent like a ferrous catalyst, especially at elevated temperatures. Here is the scheme of physisorption and chemisorption. Hydrogen atom adsorbed adsorbed by the process of physisorption and chemisorption. Now, factor influencing adsorption. The adsorption of gases is a phenomena exhibited by nearly all solid, but the quantity of gas adsorbed is influenced by several key factors. First one is nature and surface area of the adsorbent. The volume of adsorbed gas is directly proportional to the surface area of the adsorbent. Material like charcoal and silica gel, characterized by extensive porous structures, excel as adsorbents due to their large surface areas. Number two is nature of the gas. Different gases display varying degrees of adsorption on the same adsorbent at identical temperature. The adsorption tendency increases with a higher critical temperature, indicative of greater liquefaction ease. Number three is effect of temperature. Generally, adsorption is temperature sensitive. In most cases, it is an exothermic process resulting in reduced adsorption with escalating temperature. However, for endothermic adsorption process, an increase in temperature leads to enhanced adsorption. Number four is pressure. Under constant pressure conditions, gas adsorption rises with increasing pressure. At lower temperature, the adsorption of gas experiences a rapid augmentation as pressure level climbs. Activation of the solid adsorbent. Solid adsorbent activation involves enhancing the surface area through various methods such as roughening the surface, subdividing the adsorbent into smaller pieces or grain, and eliminating previously absorbed gases. Now the techniques for investigating chemisorption. Number one is X-ray photoelectron spectroscopy. XPS analyzes surface chemical composition, revealing elements and their chemical states changing in binding energy, indicate the formation of chemical bond between the adsorbate and the surface. Number two is infrared spectroscopy, IR. IR spectroscopy identifies surface functional group and detects vibrational frequency changes associated with bond formation during chemisorption. Number three is temperature programmed desorption, TPD. TBD involves heating the sample to dissolved adsorbates while monitoring desorption temperature. It helps determine the strength of adsorption bond and the types of dissolved species. Number 4 is electron energy loss spectroscopy. Electron energy loss spectroscopy through a sample loss through a sample providing information about electronic structure and facilitating the study of chemisorption. And last one is electron spectroscopy. Agar AES measures the kinetic energy of agar electron emitted during inner shell electron ejection, offering insight into surface elemental composition and changes induced by chemisorption. Now techniques for analyzing physisorption. Number 1 is Bernard-Emmett-Taylor analysis. BET determines the specific surface area by measuring gas molecule adsorption at different pressure, particularly useful for studying physisorption on porous material. Number 2, low temperature nitrogen adsorption. Adsorption isotherm of nitrogen at low temperature reveals information about surface area and pore size distribution essential for studying physisorption. Number 3 is thermogravimetric analysis TGA. TGA measures mass change in a sample with temperature, allowing with the study of physisorption through weight loss due to the desorption of weakly bound molecules. Number 4 is scanning tunneling microscopy. Astrium visualizes individual adsorbate on surface, offering insights into the spatial distribution and arrangement of physisorbed species. And number 5th, gas chromatography. GC monitors changes in gas concentration over time, providing information on the desorption of gases from a surface during physisorption. Now there is a comparison between the chemisorption and physisorption. Physisorption versus chemisorption. The adsorption process exhibits two distinct phenomena: physical adsorption, commonly referred to as physisorption, and chemisorption as chemical adsorption. Distinguishing between these two processes is often challenging due to the potential occurrence of intermediate behavior. Typically, interaction between the adsorbent surface and adsorbate involve relative weak forces such as Coulombic and dispersion forces. However, on the atomic level, there may be instances of atomic defection or atoms with the capacity to form bonds on the surface, leading to the formation of chemical bonds in a process known as chemisorption. Chemisorption tends to manifest at elevated temperatures surpassing the critical temperature of adsorbate and is often characterized by irreversibility under mild condition. It is marked by substantial interaction potentials resulting in a high adsorption heats. Nevertheless, the distinction between the physisorption and chemisorption extend beyond adsorption heats and encompassing various aspects. Physical and chemical adsorption share certain properties, with physical adsorption involving gas molecule interacting with the solid surface through van der Waals types forces influencing the adsorption characteristics. Physical adsorption is characterized by a feeble interaction between gas molecule and the solid surface. Consequently, there are no alteration to the surface during the process of adsorption measurement. Physical adsorption exhibits an exothermic nature characterized by attractive interaction forces resulting in heat release comparable to the enthalpies of the adsorbed substances condensation. The exothermicity of this process leads to an increase in physisorption with a decrease in adsorbent temperature and an increase in adsorbate pressure. The identity of the physisorbed molecule remains intact as the energy involved is insufficient to break the bond, although its geometry may undergo distortion. Physisorption is non-specific as the force at play lacks specificity. Typically, molecules do not interact with distinct adsorption center. Physisorption occur in multi-layers, allowing additional layers to be adsorbed. Atop a layer of adsorbed molecule, the initial adsorbed layer formed through direct interaction with the surface, while subsequent layers involves interaction between molecules resembling the condensation process. However, distinguishing between these processes is not always straightforward, particularly in situations where the chemisorption process is weak. In chemical adsorption, gas molecules engage with the solid surface through chemical bonds akin to physical adsorption, shaping the characteristics of the adsorption process. The interaction forces in chemical adsorption are attractive with released heat comparable to the enthalpies of formation of a chemical bond. Chemisorption involves both bond formation and breakage, resulting in enthalpy value that can be positive or negative. Due to the Robust interaction involving bond formation, chemical adsorption is confined to a monolayer, and physical adsorption may take in subsequent layers. Instance of chemical bond formation, the structure of the chemisorbed molecule differ from that in the gas phase. Now the adsorption isotherms. Adsorption isotherm play a crucial role in research related to the environmental protection and adsorption technique. The Freundlich and Langmuir isotherms are the primary methods employed for predicting the adsorption capacity of a given material. An adsorption isotherm is a graphical representation illustrating the change in the amount of adsorbate adsorbed on the surface of the adsorbent with variation in pressure at a constant temperature. Applying Le Chatelier principle, we understand that the equilibrium in a reaction shifts in the direction where stress is elevated in the context of adsorption. Applying excess pressure to the system leads to a shift in equilibrium towards a decrease in the number of molecules, thus reducing the pressure within the system. The graph also indicates that once a saturation pressure is reached, there is no further change in the amount of adsorbate adhering to the adsorbent. This occurs due to the limited surface area available for adsorption. As all the sites become occupied, any subsequent increase in pressure does not result in discernible difference. Various scientists have put forth diverse adsorption isotherm like Langmuir's isotherm and Freundlich isotherm. The above presented graph illustrates the isotherm suggested by the Freundlich. Now, Freundlich adsorption isotherm. The Freundlich adsorption model depicts the change in the amount of gas adsorbed per unit mass of solid adsorbent in response to variation in the system pressure at a constant temperature. The equation representing the Freundlich isotherm is expressed as follows. X over m is equal to xp 1 by n, where n is greater than 1, where x is the mass of the gas adsorbed, m is the mass of adsorbent, p is the pressure, and n is a constant which depends upon the nature of the adsorbent and the gas at a given temperature. Taking the log on the both sides of the equation, we get log x over m is equal to log k plus 1 over n log p. The graphical representation of this equation form a linear curve as depicted by the following plot. Now, Langmuir adsorption isotherm. Following the Freundlich adsorption isotherm, other isotherm is commonly considered the Langmuir adsorption isotherm. The Langmuir adsorption isotherm anticipate linear adsorption at low adsorption density and reach a maximum surface coverage at higher concentration of the solute metal. The Langmuir adsorption isotherm is expressed as theta is equal to Kp over 1 plus Kp. In the equation, theta represents the fraction of the surface covered by the adsorbed molecule. K is the equilibrium constant, also referred to as the adsorption coefficient. K is equal to Ka over Kd, where Ka is the rate constant for adsorption and Kd is the rate constant for desorption. P denotes the pressure. The Langmuir adsorption model is applicable in scenario of monolayer adsorption onto a homogeneous surface, particularly when there is no interaction between the adsorbed species. Applications of adsorption. Adsorption find various applications including first one, gas masks. Adsorption is implied in gas masks where poisonous gases are adsorbed on the mask's surface, preventing their encounter and ensuring the safety of a coal miners. Number two is production of vacuum. Adsorption plays a role in the production of vacuum. Traces of air are adsorbed on charcoal and subsequently removed from devices undergoing the evacuation process. Number three, mixture removal. Silica gel pellets are utilized for the adsorption of moisture in medicine and new plastic bottle. This application helps control humidity, preserving the quality of the product. Color removal in the extraction process of juice from can. Adsorption is utilized. The juice is treated with animal charcoal to remove the coloring agent, resulting in a clear liquid solution. Now, applications of Physisorption and Chemisorption. Recently, hydrogen has gained significant attention because of its potential to help address global warming. As a result, there have been substantial efforts to develop technologies for hydrogen production, transportation, storage, and conversion into usable form of energy. Hydrogen stands out for having the highest energy per unit of mass compared to other chemical fuel, offering substantial power and large-scale energy storage capabilities. It is considered an ideal solution for addressing the intermittency of renewable energy sources. However, a drawback is its low volumetric energy density. Hydrogen storage is a crucial aspect in the development and growth of hydrogen and fuel technologies, whether for portable stationary power or transportation. Hydrogen can be stored in gas, liquid, or solid state, and it remains unchanged over time if not used. This makes hydrogen an excellent choice for generating units and other mission critical energy applications. Applications of physisorption. In physisorption method, the material used must have a large surface area. Additionally, high pressures and low temperature are necessary to achieve a high capacity for storing hydrogen. This is because the energy needed to trap hydrogen through physisorption is low, around a few kilojoules per mole of hydrogen. The surface area of the material determines how much hydrogen can be absorbed through physisorption. Releasing the hydrogen that is physisorbed requires either raising the temperature or lowering the hydrogen pressure. Therefore, this technology requires a high pressure cylinder and a cooling system. Carbon-based nanoporous materials such as activated carbon, single and multi-walled carbon nanotubes, and metal organic frameworks show promise in physisorption. Here, hydrogen gas can be stored using carbon nanotubes. These materials can be optimized for hydrogen storage through chemical and physical treatment. Carbon is particularly suitable for this purpose due to its low mass densities, high surface areas, and chemical stability. Carbon nanotubes are preferred because of their lightweight and weak van der Waals forces with a binding strength less than 10 kJ per mole. Carbon nanotubes are cylindrical structures made from rolled up graphite sheets, and their hydrogen adsorption capacity depends on the size and curvature of the tubes. The direction of rolling also affects important properties such as mechanical, electrical, and thermal properties. Hydrogen adsorption on carbon materials, particularly in carbon nanotubes, offer advantages in terms of storage capacity. For example, at room temperature and 650 atm pressure, the gravimetric storage capacity is 7.75% weight, and the volumetric capacity is 0.209 kilojoule kg hydrogen per liter. In the case of single wall carbon nanotubes with a specific area of 1300 meters square per gram, the quantity of adsorbed hydrogen is 3 at 77 Kelvin. Multi-walled nanotubes are store around 1.8 to 2.6 mass percent of hydrogen under approximately 10 megapascal at room temperature. Metal organic framework materials are considered promising for hydrogen storage through physisorption. This is because they possess a high specific surface area and suitable four dimension. These materials have demonstrated gravimetric hydrogen storage capacity in the range of 5 to 9% weight and volumetric capacities between 40 to 60 gram per liter under high pressure and at 77 Kelvin. Now there is the application of chemisorption. In chemisorption technology, the material used include metallic and chemical hydrides, ammonia, and liquid organic hydrogen carriers. The key advantage of this method is its high volumetric density, which is the highest compared to other hydrogen storage technology. However, it comes with high cost and requires operating at elevated temperatures. First of all, metal hydride is a method of chemically storing hydrogen in a solid state by combining hydrogen atom with metal. This reaction occurs at high temperature with transition metals like iron, chromium, manganese, vanadium, copper, cobalt, nickel, gold, and platinum. Metallic hydrides have an exceptionally high volumetric density of hydrogen atom within the host lattice. Yet these materials are not suitable for practical application, especially in vehicles, because they have a very low gravimetric storage density. The highest known volumetric hydrogen density today is 150 kg meter cube found in density. Found in substances like magnesium ferrous hydride and aluminium boron hydride. Metallic hydrides achieve a volumetric hydrogen density of 150 kg meter cube. The drawback of this technology is that it requires activation energies higher than what can be easily supplied through hydrogen pressure. Consequently, the hydrogenation process needs to be performed separately, making it suitable for one-time application but not practical for automobile. Ammonia presents a promising alternative for hydrogen storage. With a vapor pressure of 9.2 bar at room temperature, it can be efficiently stored in cost-effective pressure reserves. Notably, ammonia contains substantial hydrogen content, 17.65%, resulting in a high volumetric density that is 4.5 times greater than that of a liquid hydrogen. Additionally, ammonia is well established for amalgamation and distribution, and its combustion produce no carbon dioxide emission. It can be blended with existing fuels and burned effectively. However, the hydrogen liberation process requires high energy expenditure. Safety precautions are crucial due to ammonia being a poisonous gas, and traces of ammonia may persist in the hydrogen after decomposition. Chemical hydrogen storage involve the absorption of hydrogen by a specific material in water, where both water and the material act as storage medium for the absorbed hydrogen. Chemical hydride, which can be either solid or liquid, exhibit storage capacity ranging from 6 to 8% weight and possesses higher energy densities compared to metal hydride when operated at mild temperatures. Key examples of chemical hydride include borohydrides and ammonia borane. Notably, chemical hydride offer favorable volumetric capacities at suitable temperature due to their composition of lighter elements. However, a notable drawback is the need for high activation energies during the absorption process, surpassing the energy provided by hydrogen pressure. Consequently, hydrogen must be carried out independently, making chemical hydride more suitable for one-time use, preferably avoiding the absorption-desorption cycle typical of metal hydrides. Additionally, the produced output needs to be regenerated off-board the vehicle due to the irreversibility of dehydrogenation reactions. The use of liquid organic hydrogen carriers stands out as an appealing and promising technology for hydrogen storage. This approach comprises two key stages. The initial stage involves charging hydrogen into liquid organic hydrogen carriers through a catalytic hydrogenation reaction, while the subsequent stage entails discharging hydrogen via catalytic dehydrogenation reaction. Liquid organic hydrogen carriers are material capable of undergoing a reversible hydrogenation-dehydrogenation process while in a liquid state. Notably, this method allows for both hydrogenation and dehydrogenations to occur at the same temperature. The primary advantage of liquid organic hydrogen carriers include high gravimetric and volumetric density, ease of storage and transportation of generated hydrogen at ambient temperature, and a lower level of operational and investment risk, as existing fuel infrastructure can be repurposed for storing and transporting hydrogen in the form of liquid organic hydrogen carriers. Furthermore, liquid organic hydrogen carriers charging involves catalytic hydrogenation under high hydrogen pressure, while hydrogen release from the liquid organic hydrogen carriers occur under low hydrogen pressure, under 5 bar, reducing the risk of explosion due to the low amount of hydrogen in the liquid organic hydrogen carrier system. Thank you.